Welcome to the Leap into Finance YouTube channel, where we offer insights, tools, and resources to help finance professionals advance their careers. Today, let's explore statistical measures within the quantitative methods section of the CFA Level 1 curriculum. In this video, we'll dive into advanced topics such as measures of central tendency, location, and dispersion, featuring worked examples to help you master the concepts and tackle challenging exam questions. We'll be using the Texas Instruments BA2 Plus Professional Calculator for all calculations. So let's get started. 1. Measures of central tendency. Let's start with an overview of central tendency. Central tendency measures give you an idea of the center or typical value of a dataset. The most common measures are the mean, median, and mode. 1. Arithmetic mean. The arithmetic mean is the most commonly used measure and is appropriate when the dataset does not have outliers or when we assume the data are normally distributed. The formula for the population mean is mu equals 1 over n times the sum from I equals 1 to n of x sub I, where n is the number of observations and x sub I are the values in the dataset. For a sample, the formula for the sample mean is x bar equals 1 over n times the sum from I equals 1 to n of x sub I, where n is the number of observations in the sample and x sub I are the values in the sample. Let's consider a population of 12 observations. 10, 12, 15, 18, 20, 22, 25, 27, 30, 32, 35, 40. We'll use the Texas Instruments BA2 Plus Professional to calculate the mean. Let's go through the steps. Before entering any data, always clear the memory on your BA2 Plus to avoid any previous calculations from interfering. Step 1. Clear the calculator's memory and enter the data for the population. Turn on the calculator. Press second, then data. This accesses the data list. Press second, then CLR work to clear the list. Enter the 12 values of the population one by one. Press 10 and then enter to input the first data point. Press the down arrow key to move to the next entry and continue inputting the rest of the data. 12, 15, 18, 20, 22, 25, 27, 30, 32, 35, 40. Step 2. Compute the population mean. Now that we have entered the data, we will calculate the mean. Press second, then stat to bring up the summary statistics. Look for the x-bar value, which represents the mean on the display. This is the population mean, since we are working with all the data points. The BA2 Plus will display x-bar equals 23.833, which is the arithmetic mean of this population. Step 3. Compute a sample mean. Now let's take a random sample of 5 observations from this population. 10, 15, 22, 30, 35. To calculate the sample mean, follow the same steps as above, but with a different dataset. Press second, then data again to access the data list. Clear the previous data by pressing second, then CLR work to clear the list. Enter the new 5 data points, 10, 15, 22, 30, and 35. Press second, then stat to access the statistics menu. Look for the x-bar value, which represents the sample mean, on the display. It will show x-bar equals 22.4, which is the mean of this sample. So, the population mean is 23.833, and the sample mean is 22.4. 1-2. Weighted mean. The weighted mean is used when different data points have different levels of importance or weight. The formula is weighted mean equals the sum from I equals 1 to n of w sub I times x sub I, divided by the sum from I equals 1 to n of w sub I, where w sub I is the weight associated with each observation. Example, consider the following data and weights. Data, 10, 12, 15, 18. Weights, 1, 2, 3, 4. The weighted mean is calculated as weighted mean equals the sum of 1 times 10, plus 2 times 12, plus 3 times 15, plus 4 times 18, divided by the sum of 1 plus 2 plus 3 plus 4. This gives us 10 plus 24 plus 45 plus 72, divided by 10, which equals 15.1. 1-3. Harmonic mean. The harmonic mean is appropriate for situations like averages of rates or ratios, especially when you want to avoid giving undue weight to large values. The formula is harmonic mean equals the sum from I equals 1 to n of 1 over x sub I, all divided by n, which is the same as n divided by the sum from I equals 1 to n of 1 over x sub I. Example, for the values 2, 4, 6, 8, the harmonic mean is calculated as harmonic mean equals 4 divided by the sum of 1 over 2, plus 1 over 4, plus 1 over 6, plus 1 over 8, which equals approximately 4 over 1.0417, rounded to 3.84. 1.4. Geometric mean. The geometric mean is the average of a set of numbers calculated by multiplying them together and then taking the nth root, where n is the number of values. It's typically used when the data represents growth rates or returns, especially over time. It's particularly helpful in situations where numbers are compounded, like investment returns. In finance, the geometric mean is used to find the average rate of return or growth over time. It is appropriate for time series data or growth rates. The formula for geometric mean is geometric mean equals the product from I equals 1 to n of the quantity 1 plus or sub I, raised to the power of 1 over n minus 1. Example, compute the geometric mean return for a set of returns over 4 years. 10%, minus 5%, 8%, 3%. Solution. Step 1. Convert the percentages to decimal form. Returns. 0.10, minus 0.05, 0.08, 0.03. Step 2. Add 1 to each value to represent the total growth, since geometric mean is used for growth rates. A growth factors: 1.10, 0.95, 1.08, 1.03. Step 3. Multiply all the growth factors together. 1.10 times 0.95 times 1.08 times 1.03 equals 1.1625. Step 4. Take the fourth root, since there are 4 data points, to find the geometric mean. 1.1625 raised to the power of 1/4 equals 1.0384. Step 5. Subtract 1 and convert back to percentage form. 1.0384 minus 1 equals 0.0384, or 3.84%. Thus, the geometric mean return is 3.84%. When to use the geometric mean? When dealing with growth rates, like investment returns. When you want to find the average rate of return over time, or the average compound growth rate. It is more appropriate than the arithmetic mean when data is subject to compounding. 1.5 Trimmed mean. A trimmed mean is calculated by removing a certain percentage of the smallest and largest data points in the dataset before calculating the average. This is particularly useful when there are outliers that might distort the mean. Formula for trimmed mean. Trimmed mean equals the sum of x sub I, after removing the extremes, divided by the quantity n minus k, where x sub I are the remaining data points after trimming. K is the number of observations removed from each end, e.g., removing 10% from each end. Example, data 1, 2, 3, 4, 5, 6, 100. Calculate the trimmed mean by removing the lowest one value and the highest one value, that is, one trimmed value from each end. Step 1. Sort the data. Sorted data 1, 2, 3, 4, 5, 6, 100. Step 2. Remove the lowest and highest values. Trim data 2, 3, 4, 5, 6. Step 3. Calculate the mean of the remaining data. Trimmed mean equals 2 plus 3 plus 4 plus 5 plus 6, divided by 5 equals 20, divided by 5 equals 4. Thus, the trimmed mean is 4. When to use the trimmed mean? When the data contains outliers or extreme values that could skew the mean. It is useful when you want to get a more robust average that is less sensitive to extreme values. 1.6. Winsorized mean. A winsorized mean is similar to a trimmed mean, but instead of removing the extreme values, you replace them with the next nearest value. This method is often used to limit the impact of outliers without completely discarding them. Formula for winsorized mean. Winsorized mean equals the sum of x sub I, after replacing extreme values, divided by n, where the extreme values are replaced with the next nearest value. Example, using the same dataset from the trimmed mean example, data 1, 2, 3, 4, 5, 6, 100. Let's calculate the winsorized mean by replacing the lowest value, 1, with the next smallest, 2, and replacing the highest value, 100, with the next largest, 6. Step 1. Replace the extremes. Winsorized data 2, 2, 3, 4, 5, 6, 6. Step 2. Calculate the mean of the winsorized data. Winsorized mean equals 2 plus 2 plus 3 plus 4 plus 5 plus 6 plus 6, divided by 7, equals 28 divided by 7 equals 4. Thus, the winsorized mean is 4. When to use the winsorized mean? When you want to limit the influence of outliers, but still include them in the analysis. It's useful when you don't want to completely discard extreme values, but want to reduce their impact on the average. 2. Measures of location and dispersion. 2.1. Range. The range is the difference between the largest and smallest values in the dataset. It is a simple measure of dispersion. Range equals max value minus min value. For the dataset 10, 12, 15, 18, 22, the range is 22 minus 10 equals 12. 2.2. Mean absolute deviation MAD. MAD is a measure of the dispersion, spread, of data points around the mean. Unlike variance or standard deviation, which square the deviations, MAD takes the absolute value of the deviations. Formula for mean absolute deviation. MAD equals 1 over n times the sum from I equals 1 to n of the absolute value of x sub I minus x bar, where x sub I are the individual data points. X bar is the mean, average of the data set. N is the number of data points. Example, stock returns for 5 periods, 5%, minus 2%, 1%, minus 3%, 4%. Answer, mean equals 1 and mean absolute deviation, MAD, equals 2.8. 2.3. Sample variance and sample standard deviation. The sample variance measures the spread of the data points around the sample mean. The formula for sample variance is S squared equals the sum from I equals 1 to n of x sub I minus x bar squared divided by n minus 1, where x bar is the sample mean. Let's take the sample. 10, 15, 22, 30, 35. Step 1. Enter the data. Press second, then data to enter the data list. Clear any previous data using second, then CLR work. Enter the new data points, 10, 15, 22, 30, and 35. Step 2. Calculate the sample variance and standard deviation. Press second, then stat to bring up the statistics menu. The calculator will display the summary statistics. Scroll down to find SX, the sample standard deviation, and SX superscript 2, the sample variance. The sample standard deviation will be displayed as S sub x equals 10.31, and the variance is the square of the standard deviation. Variance equals 106.3. 2.4. Coefficient of variation CV. The coefficient of variation, CV, is the ratio of the standard deviation to the mean and is used to compare the relative risk of different datasets. The formula is coefficient of variation, CV, equals the standard deviation divided by the mean, times 100. Using the sample from above, mean equals 22.4, standard deviation equals 10.31. The coefficient of variation is CV equals 10.31 divided by 22.4 times 100 equals 46.03%. 2.5. Target downside deviation. The target downside deviation is a risk measure that only considers negative deviations from a target value, usually the mean or a benchmark return. It is useful for evaluating downside risk in investment portfolios. The formula is target downside deviation equals the square root of the sum from I equals 1 to n of the maximum of 0 and the quantity mu minus x sub I, squared divided by n minus 1. Note that the denominator in this formula is n minus 1 to correct for bias in the variance estimation, as we are calculating the sample target downside deviation, that is, working with a sample of returns rather than the entire population. This adjustment is similar to the one used in the sample standard deviation calculation. For the population downside deviation, we would use n in the denominator. Example, monthly returns for an investment over a 5-month period. Returns, x sub I 5%, minus 2%, 1%, minus 3%, 4%. Target return, mu 2%. Step 1. Determine the deviations from the target, 2%, for each data point. For each return, subtract the target return, 2%, and take the maximum of 0 and the result. This ensures that only returns below the target are considered. The results are summarized in the table below. The deviations calculated as max, 0, mu minus x sub I, are 5%, no deviation, greater than target, so it's 0%. Minus 2%, deviation of 4%, since 2% minus 2% equals 4%. 1%, deviation of 1%, since 2% minus 1% equals 1%. minus 3%, deviation of 5%, since 2% minus 3% equals 5%. For percent, no deviation greater than target, so it's 0%. Step 2, square the deviations from the target. The results are summarized in the table below. Step 3, calculate the average of the squared deviations. Divide the sum of squared deviations by n-1 is equal to 4 degrees of freedom. The average squared deviation is 10.5. Step 4, finally, take the square root of the average squared deviation to obtain the target downside deviation, TDD. The target downside deviation, TDD, is approximately 3.24%. In statistics, quantiles divide a data set into equal parts, allowing us to understand the distribution of the data. They are helpful in summarizing and interpreting the spread and central tendency of data. Key quantiles include quartiles, quintiles, deciles, and percentiles. These values are useful for understanding how data points are distributed relative to one another. Quantiles can be especially useful in finance, where measures like the interquartile range and percentiles provide insight into risk and return, making them essential tools for the CFA Level 1 exam. Definitions. Quartiles divide data into 4 equal parts. The 3 quartiles are: Q1, first quartile. 25% of the data points lie below it. Q2, second quartile or median. 50% of the data points lie below it. Q3, third quartile. 75% of the data points lie below it. Quintiles divide data into 5 equal parts. There are 4 quintiles: Q1, Q2, Q3, and Q4. Deciles divide data into 10 equal parts. The key deciles are D1, D2, D9, with D1 representing the 10th percentile and D9 the 90th percentile. Percentiles divide data into 100 equal parts. The P1 percentile corresponds to the first percentile, P50 is the median, and P99 corresponds to the 99th percentile. Interquartile range, IQR, is the difference between the third quartile, Q3, and the first quartile, Q1 IQR equals Q3 minus Q1. It is a measure of statistical dispersion, providing an indication of the spread of the middle 50% of the data. Use the position formula to determine a quantile. The position formula for any quantile is: position of the quantile equals P times the quantity n plus 1 divided by 100, where P is the percentile, for example, 25 for Q1, 50 for Q2, etc. N is the number of data points. Worked examples. We'll now demonstrate how to calculate quartiles, quintiles, deciles, and percentiles using a sample dataset on the BA2 Plus calculator. The calculator doesn't have built-in functions for quantiles, so we'll use sorting and manual calculations. Example dataset: 2, 4, 5, 6, 8, 10, 12, 14, 16, 18. N equals 10. Quartiles: Q1, Q2, Q3 quartiles. Step 1. Sort the data. Sorted data: 2, 4, 5, 6, 8, 10, 12, 14, 16, 18. Step 2. Calculate the quartiles. Q1, first quartile, 25th percentile position of Q1 equals 25 times the quantity 10 plus 1, divided by 100, equals 25 times 11 divided by 100, equals 2.75. Since 2.75 is not a whole number, we interpolate between the second and third data points, 4 and 5. Interpolation: Q1 equals 4 plus 0.75 times the quantity 5 minus 4, equals 4 plus 0.75, equals 4.75. Thus, Q1 equals 4.75. Q2, second quartile, 50th percentile, also known as the median. Position of Q2 equals 50 times the quantity 10 plus 1, divided by 100, equals 50 times 11 divided by 100, equals 5.5. Since 5.5 is not a whole number, we interpolate between the 5th and 6th data points, 8 and 10. Interpolation: Q2 equals 8 plus 0.5 times the quantity 10 minus 8, equals 8 plus 1, equals 9. The median is 9. Q3, third quartile, 75th percentile position of Q3 equals 75 times the quantity 10 plus 1, divided by 100, equals 75 times 11 divided by 100, equals 8.25. Since 8.25 is not a whole number, we interpolate between the 8th and 9th data points, 14 and 16. Interpolation: Q3 equals 14 plus 0.25 times the quantity 16 minus 14 equals 14 plus 0.5 equals 14.5. The third quartile, Q3, is 14.5. Thus, the quartiles are Q1 equals 4.75, Q2 equals 9, and Q3 equals 14.5. The quintiles. Now, we calculate the quintiles, divide the data into 5 equal parts. P20, 20th percentile position of P20 equals 20 times the quantity 10 plus 1, divided by 100, equals 20 times 11, divided by 100, equals 2.2. Since 2.2 is not a whole number, we interpolate between the second and third data points, 4 and 5. Interpolation P20 equals 4 plus 0.2 times the quantity 5 minus 4, equals 4 plus 0.2, equals 4.2. That is, the 20th percentile P20 is 4.2. Using similar calculations, the values for the other quartiles are as follows. P40, 40th percentile, equals 6.8. P60, 60th percentile, equals 11.2. P80, 80th percentile, equals 15.6. The deciles. We'll calculate a couple of deciles to see how they work. D1, 10th percentile. Position of D1 equals 10 times the quantity 10 plus 1, divided by 100, equals 10 times 11, divided by 100, equals 1.1. Since 1.1 is not a whole number, we interpolate between the first and second data points, 2 and 4. Interpolation. D1 equals 2 plus 0.1 times the quantity 4 minus 2, equals 2 plus 0.2, equals 2.2. Thus, the first decile is 2.2. D5, 50th percentile, or median, we already calculated this earlier. D5 equals 9, same as Q2, the median. Percentiles. Let's demonstrate how to calculate a percentile using an example. P90, 90th percentile position of P90 equals 90 times the quantity 10 plus 1, divided by 100, equals 90 times 11, divided by 100, equals 9.9. The 90th percentile is 17.8. 27. Covariance. Covariance is a statistical measure that indicates the direction of the linear relationship between two variables. In other words, covariance tells us whether two variables tend to increase or decrease together. However, the magnitude of covariance is difficult to interpret on its own because it depends on the scale of the variables. If the covariance is positive, both variables tend to increase or decrease together. If the covariance is negative, one variable tends to increase while the other decreases. If the covariance is 0, the variables are uncorrelated, meaning that there is no linear relationship between changes in one variable and changes in the other. The formula for covariance between two variables x and y is covariance of x and y equals the sum from I equals 1 to n of the product of the difference between x sub I and the mean of x, and the difference between y sub I and the mean of y, divided by n, where x sub I and y sub I are individual data points for variables x and y. X bar and y bar are the means of variables x and y. N is the number of data points. By expanding the formula and applying algebraic manipulation, we get the simplified formula. COV of x and y equals 1 over n times the sum from I equals 1 to n of x sub I times y sub I minus x bar times y bar. Example, x 2, 4, 6, 8, 10, and y 1, 3, 5, 7, 9. Let's go through the steps using the Texas Instruments BA2 Plus calculator to compute covariance. Step 1. Input the data into the calculator. 1. Clear the memory. Press second then data, then press second then CLR work to clear any previous data in the memory. 2. Enter the data for variables x and y. 3. Press second then stat to go to the statistics menu. 4. Press the down arrow to get the values for x bar 6, y bar 5, sum of products of x sub I and y sub I, 190, and n 5. 5. Substitute these values into the simplified formula. COV of x and y equals 190 divided by 5 minus 6 times 5 equals 38 minus 30 equals 8. 28. Correlation. Correlation is a statistical measure that describes the strength and direction of a relationship between two variables. It helps to determine how changes in one variable are associated with changes in another. A correlation can range from -1 to +1. +1 indicates a perfect positive relationship. -1 indicates a perfect negative relationship. 0 means no linear relationship exists. However, correlation does not imply causation. Just because two variables are correlated doesn't mean that one causes the other. This is a critical point to understand, as it's easy to fall into the trap of assuming causality when correlation is observed. A spurious correlation occurs when two variables appear to be related, but are actually influenced by a third, hidden factor. Formula for correlation coefficient. The formula to calculate the Pearson correlation coefficient, R, between two variables x and y is, where n is the number of data points. X sub I and y sub I are the individual data points for each variable. You don't need to memorize this formula because the calculators allowed on the CFA exam have the correlation coefficient function built in. Let's work through an example. Data set x, 50, 29, 130, 60y, 73, 50, 76, 56, 62. In this example, we will explore correlation using a data set where the correlation is less than 1, demonstrating a less than perfect relationship between the two variables. As before, we'll use the Texas Instruments BA2 Plus Professional Calculator to compute the Pearson correlation coefficient. 1. Clear the calculator's memory and enter the data. Press second, then data to access the data input screen. Press second, then CLR work to clear any stored data. Enter the x and y values by pressing the down arrow. 2. Calculate the correlation coefficient. Press second, then stat to access the statistics menu. Press the down arrow until the correlation coefficient, R, is displayed. For this example, the correlation coefficient is calculated as R equals 0.816, which indicates a strong positive linear relationship between x and y, but not a perfect one. The correlation is less than 1 because the data points do not follow a perfectly linear pattern. The correlation coefficient between two variables can also be calculated using the following formula. R equals the covariance of x and y, divided by the product of the standard deviation of x and the standard deviation of y. Example, data, standard deviation of variable x, sigma sub x 10%. Standard deviation of variable y, sigma sub y 15%. Covariance between variable x and y, COVXY, equals 0.0050. Compute the correlation coefficient between x and y. Substitute the values into the correlation formula to get 0.333. In this video, we've covered essential statistical measures from the quantitative methods section of the CFA Level 1 exam, focusing on measures of central tendency, location, and dispersion. Measures of central tendency. Arithmetic mean, the simple average of a data set. Weighted mean, an average where each data point has a different level of importance. Harmonic mean, useful for averaging rates, especially when the values are inversely proportional. Geometric mean, the average of products, used for growth rates or returns over time. Trimmed mean, a mean calculated after removing a certain percentage of the extreme values, outliers. Winsorized mean, similar to a trimmed mean but replaces extreme values with the nearest remaining values instead of removing them. Measures of location and dispersion. Range, the difference between the maximum and minimum values in a data set. Mean absolute deviation, MAD the average of the absolute deviations from the mean, providing insight into data spread. Variance, a measure of how far each data point is from the mean, calculated as the average of squared deviations. Standard deviation, the square root of variance, offering a more interpretable measure of dispersion in the same units as the data. Coefficient of variation, CVA standardized measure of dispersion, calculated as the ratio of the standard deviation to the mean, useful for comparing the relative risk of different data sets. Quantiles. A quantile is a value that divides a dataset into equal intervals, with each interval containing the same proportion of data points. Target downside deviation. TDD, a measure of risk that only considers negative deviations from a target return. Correlation. A statistic that measures the strength and direction of a linear relationship between two variables. These topics are essential for analyzing data and assessing risk in finance, and mastering them is crucial for success in the CFA Level 1 exam. Preparing for this exam shows your commitment to advancing your career. To further support your endeavor, we offer additional resources that will accelerate your progress. Explore the links below for carefully curated resources available on Amazon, including essential tools to help you excel in your exams. One highly recommended option is the Leap into Finance notebook, specifically crafted to keep you organized and on track. Visit leapintofinance.com for access to job opportunities, scholarships, and exclusive career resources that will propel your career forward. Thanks for watching. Don't forget to hit the like button and subscribe for more exam tips, concept reviews, expert insights, and career success strategies. Have questions or feedback? Drop them in the comments below. We'd love to hear from you. Be sure to explore the videos on your screen for more high-quality content from Leap into Finance to further support your finance journey. Stay focused, stay determined, and keep leaping into finance.